So page 469, make sure you got a pencil. You will need a calculator today. So if you have a calculator, yeah, go ahead and grab one. We're gonna be doing a lot with fractions today and simplifying fractions and things like that. So definitely get yourself 469. Get yourself a calculator. The scientific ones are going to be better to use today than the graphing ones, so I'm actually going to go get a scientific calculator as well. All right. Fraction buttons on these ones are very easy to use. So, there we go. Oh, by the way, tomorrow's dress-up day, 4th of July. So 4th of July, you can go like barbecue style. If you have a shirt with like fireworks on it, that'd probably be fine too. So, or if you just have like something red, something white, and something blue, you can just wear all those things together. You know, that'll be fun. But you get spirit points for your class, and whichever class wins the spirit competition for this school year gets a field trip. So, you know, there's a reason to dress up. All right. So today, similar polygons. We'll try to work through these pretty quickly. I don't think today's lesson is going to be too terribly complicated. Just pay close attention. I think you'll be fine. If you have questions, let me know. So a dilation, we talked about this already. A dilation is a type of similarity transformation. Just make something bigger or smaller. A similarity transformation is a transformation composed of a dilation or a dilation and a rigid motion. So making it bigger or smaller and then potentially moving it around. Two figures are similar polygons if one can be obtained from the other by a dilation or a dilation with one or more rigid motions. I know I'm talking fast, but this is what we did in the warm-up. When two polygons are similar, their angles and sides are related. Specifically, here's our first theorem. Two polygons are similar if and only if their corresponding angles are congruent. So similar figures have the exact same angle measurements no matter what, something larger or something smaller. Think about two squares, right? If you have a really tiny square and you have a really big square, all four corners are all 90 degrees between those two squares. It's only the side lengths that are different. So similar figures have congruent angles. And the corresponding side lengths, here we go. Here's what we're going to be dealing with a lot today. They are proportional. Proportional just means you can set up a fraction between the two different sizes of the different shapes, and you'll end up with the same fraction when you reduce those fractions. So, like congruence, similarity is reflective, symmetric, and transitive. That's what we were dealing with, like with proofs and things like that. So, reflexive, symmetric. Symmetric just means like you can flip around a statement and it means the same thing. Symmetric means something would be similar to itself. Transitive means if the first thing is similar to the second and the second is similar to the third, then the first is similar to the third. So those are kind of like the ideas of proofs that we were using. So, oh, and actually, yeah, right here. That's actually what I was just talking about. It actually tells you the properties right here anyway. Cool. So reflexive, something is similar to itself. Symmetric, you can flip around the order. And then transitive, first similar to the second, second similar to the third, first similar to the third. So those are the properties we've used before. They also work with similarity. So example one, let's move down to example one. This one says that ABCD is similar to PQRS. This symbol right here means is similar to. This is going to be really important, by the way, to know this symbol. So everybody take a look, please. Everybody listen. Listen up. Pay attention to this symbol. That means is similar. Meaning these two shapes have the exact same shape, but they are different sizes. That's what that means. So ABCD is similar to PQRS. It does not tell us what kind of shapes they are, although they appear to be kites. We don't know exactly or not whether they're kites or not. So list all pairs of congruent angles and write a proportion that relates the corresponding sides. So here's what we need to do. This kind of goes back to corresponding polygons or corresponding parts of polygons, and that means that the order that these two things are written in actually really matters. Angle A on the large one corresponds to angle P on the small one. So the first letter corresponds to the first letter. First angle corresponds to this angle here. Second one, B, corresponds to angle Q. Third one, C, corresponds to angle R. And the last one, angle D over here, corresponds to angle S over here. So what we're going to be able to say, and it actually color codes these things right here. Angle A is congruent to what? Angle P. You got it. Angle B is congruent to angle Q. Angle C is congruent to angle R. And then angle D is congruent to angle S. So the order definitely matters. And they even went with colors here too. So dark blue congruent to dark blue, orange congruent to orange, green, green, blue, blue. And then for proportion, kind of wish we would have written these on our own. However, we also have to write a statement of proportionality for all four side lengths from each one. So side length AB on the first one, and you can just use two letters here. From A to B corresponds P to Q on the other one. That's why AB is over PQ. So the length of AB in relation to the length of PQ is the same as the length of BC in relation to QR, which is the same as the length of CD in relation to RS, which is the same as the length of DA in relation to the length of SP. For example, I'm just going to give you some numbers here real quick, just to make sure that this is like completely understood. Let's say that this length is 10, and we'll just make it a kite. We'll say that length is 10 as well. And we can say that, let's say DC is, just trying to think of nice numbers we can use here. I'll say 16. And that this one is also 16. And PQ is 5, PS is 5, QR is 8, and SR is 8. So if you think about how these numbers relate, what we're saying here is if we actually use the numbers down here instead of the names of the sides, what's the length of AB that we just said here? AB? Yeah, 10. Okay. So that'll be 10 over, what's the length of PQ? 5, okay, equals BC, which is 16, over QR, which would be what? What's the length of QR according to what we just wrote? These are just random numbers we threw in, but 8, okay, so 16 to 8, and then CD is a length of 16, RS is a length of 8, DA is a length of 10, and SP is a length of 5. So what we're saying is that all of these ratios, all of these fractions are actually equal to each other. What's 10 divided by 5? 2. What's 16 divided by 8? 2. That one's 2. That one's 2. So they all have a scale factor of 2 to 1. The larger one has lengths that are twice the length of the smaller one. So that's what it means that all of the side lengths are in proportion with one another. Anytime you test it, if you have numbers, all of the numbers should simplify to the exact same thing. All of these simplify to equal 2 or 2 over 1. So questions on that? Yeah. Turn the page. Let's keep going. So what I want you to do is take 2 minutes. I'm giving you 2 minutes. I want you to list all of the congruent angles, and I want you to make a list of all the sides that are in proportion with one another. So take 2 minutes on that. List all the congruent angles, write a proportion that relates all the corresponding sides. Ready, set, go. 2 minutes. So 55 after. Now, we'll go with, yeah, 55. And just a reminder, for me, it's all like the way that I find this to be easier is not actually looking at the shapes. It's actually using the similarity statement. That makes it easier for me. Let's put our phones away. Working on the check step on the top of page 470. Yeah. Yeah. All right, let's take a look here. So, 3. Angle N is congruent to which angle? U. Good. Angle U. All right. Listen up. So angle N is congruent to angle U. And I think it's a lot easier to use the similarity statement than to use the actual images. Because this one is like, I think this one is rotated. Like, it's a different rotation of it. But if you look here, N corresponds to U. All right. So Yvonne, angle P is congruent to what? Angle V. Angle V. You got it. Yeah, it's a V. You got it. Aaron, angle Q is congruent to S. Yeah, angle S. All right. And then Leo, angle R congruent to angle T. Good. V, right? P goes to V. Yeah. Yep. All right. So then, Caden, I'm gonna go with. We'll start with NP. Corresponds to what? UV. Okay. You didn't have to write it in this order. As long as you have all 4 sides, you're good to go. Now that is going to be the same as, let's go with Zach, PQ over what? What's that? VS. PQ would be the same as VS. Good. Which is equal to, let's say, QR. Cleo, what does QR correspond to? ST. Nice. And then Caitlin, NR corresponds to what? UT. Cool. So those are all 4 pairs of sides being shown to be in proportion with one another. Any questions as to how we wrote this statement here? All good? Okay. Knowing how things correspond, you have to know that before you can actually determine if things actually are similar or not, which is the next thing we're going to do. So, problem number 2, or example 2. We're going to identify similar polygons. So first of all, we have to determine, well, we're going to determine if triangle NQP is similar to triangle RST. If it is, find the scale factor and explain your reasoning. So, step 1 tells you to compare the corresponding angles. Now, you can do that. You don't necessarily have to do that. Because as long as all 3 pairs of sides have the same ratio between the 2 triangles, then it's going to be similar no matter what. But because we have 2 pairs of congruent angles and triangles are 180, so if this is, if this is 80 and that's 40, that would be 120 for the 2 of them, which means that this last one has to be 60 for both of them. So if 2 of them if 2 angles are the same between 2 triangles, then the third angles also have to be exactly the same, because that's how subtraction works and that's how triangles work. There's also this thing called the third angle theorem, which we didn't talk about, but it is a thing. And it's exactly what I just said. If you have 2 congruent angles between 2 triangles, then the third angles have to be congruent. So yeah, all the angles are congruent. And so now we're going to test the corresponding sides. And you don't actually have to do anything on this one because the math is already done for you. But we have to check all 3 sides. So NQ corresponds to RS. NQ is 12.5. RS is 10. So what I want you to do is take your calculator, open up a fraction, and type in 12.5 over 10. And it should just automatically simplify that to be 5/4, and mine didn't, which means I need to change something on my mode. So if you're getting 1.25 instead of 5/4, we need to change the mode of our calculator. So if you click on the mode button right next to the second, oh, it does say math print. That's weird. So we're good there then. So hit quit. Just push the button above enter then. If it says 1.25, just hit the button above enter and it should take it to a fraction, 5/4. So if it gives you a decimal, just push the button above enter, the little left, right arrow button, and it'll switch it back to a fraction. So 5/4. And if you do the same thing, 11.5 over 9.2, oh, the fraction button, did you find it, Yvonne? The fraction button, you got it? Okay. So if you do 11.5 over 9.2, it'll probably give you decimal, but then if you push the left, right button right above enter, it'll say 5/4. They're all 5/4, which means that those two are similar figures. So because the corresponding angles are congruent and the corresponding sides are proportional, they all end up simplifying to a fraction of 5/4. That means that the triangles are similar. And with a scale factor, here we go. Now we've got to talk about scale factor from RST to NQP. Is RST the larger or the smaller one? Is triangle RST the larger or the smaller one? Small. Okay, so if we're going scale factor from the smaller to the larger, that means it's getting bigger, right? And so there's a couple ways that we could do this. We could say from RST to NQP, because NQP is the bigger one and we're starting here, we need to multiply by a number that's bigger than 1. 5/4 is bigger than 1. And so it's 1.25. So if you take this one and you multiply by 1.25, you get that one. It enlarges it by a little bit. Now, if you're trying to figure out the scale factor from NQP to RST, that would actually be different because we'd be going from the large one to the small one. So does anybody think they know the scale factor from NQP to RST? If this one to this one is 5/4, any thoughts about how to get from this one to this one? So 5/4 is going to make the triangle larger. So if you take this one, yeah, you both had it, 4/5. So if you flip it over, to get from this one to this one, the scale factor is 4/5 or 0.8. If you go with the decimal. So here to here, that number, 4/5 or 0.8 is smaller than 1, which makes this one smaller by multiplying it by 0.8. This one gets larger by multiplying it by 5/4 or by 1.25 to get from here to here. So if it asks you to write a scale factor from one to the other, you need to know which one to which other one. Are you going from small to large? If you are, then the number needs to be bigger than 1. If you're going from large to small, you need to know that too, because that number needs to be less than 1, but still greater than 0. So let's take a look. Determine whether or not quadrilateral is ABCD is similar to quadrilateral EFGH. If so, find the scale factor, explain your reasoning. So we're going from ABCD to EFGH. So ABCD is the smaller one, EFGH is the larger one. So if they are similar, the scale factor would need to be a number bigger than 1 because we're going from the small one to the large one. But we have to determine if they're similar. All the angles are 90, so we know the angles are congruent, so that's a good thing. But we also have to figure out if we have proportionality with the side lengths. So if I was to say 10 here from this one, what would I put that over on the other shape? 10 would go over what? From the other one. So from ABCD, if I choose 10, what would that go over from the other one? Would it go over 12 or 14? 14, yeah. Because this is the length from D to C. So this is DC over, and if you look here, DC would be HG, which equals 10/14. What does 10/14 reduce to? And you can type that into your calculator. 10/14 is a fraction, it'll give you an answer. Or you can just divide each number by 2. 5/7, yeah. So that's a ratio of 5 to 7. So now we need to test 2 more. We can test BC to FG. which numbers would be 8 over 12. 2/3, okay. Are they similar? No, they're not similar. They're both rectangles, but they're not similar. So we just say not, and then we can use the similar symbol, and we're good. If they were similar, the fractions would have to reduce to the exact same value. They didn't. It's not similar. Good so far? Cool. We're like halfway through already. Let's keep going. So, talking about example 3. This diagram here, it says find the value of y. So now we're going to get into some algebra. So it says they are similar, first of all. In the diagram, WXYZ is similar to PQRS. So you don't have to determine whether or not it is. It is. It tells you that. Find the value of y. So now we have to set up a proportion, meaning we have to set two fractions equal to each other and then solve. So the two lengths that we're provided with over here are WZ and ZY. And the two lengths we have over here are SP and RS. So if you look at WZ is 16. And if you look here, from W to Z on this one corresponds to PS over here, which is 12. So 16 over 12, that'll be our first fraction. Because they are similar, then the ratio of 16 to 12 has to be equal to the ratio of YZ over RS. YZ is 5y minus 2. Put that over RS, which is 6. So they are going to be proportional. So 16/12 is equal to 5y minus 2 over 6. Then we just use our proportion solving, which is to multiply, cross multiply. So if you cross multiply, 16 times 6 goes that way, which is going to be here, which equals 96. And then with the other one, because there's a 5y minus 2, that's actually a group, which is why it's showing that these are in parentheses, which means you need to use the distributive property. So it'd be 12 times 5y. What's 12 times 5? 60, okay. So that's going to be 60y times 12 minus 2, which will be minus 24. And then it just tells you on the right side here, add 24 to each side. So we know we got that number right. So if you add 24 to 96, what do you get? So we're going to add 24. So plus 24 here. Those are going to cancel. Plus 24 here. What's 96 plus 24? 120. All right. And then we divide both sides by 60. What's 120 divided by 60? 2. There you go. Y equals 2. So solving a proportion most of the time includes cross multiplication at some point in that process. If you have adding or subtracting on either a numerator or denominator, you do need to use the distributive property. So that's kind of the big thing to remember here. So try out the check one right underneath it. Solve for X. I'll give you 2 minutes on this, check one down here as well. So 2 minutes on this one, and we'll double check, see how we did. Sets up real similarly to what we just did. And we got the next page with 2 more problems on it, and that's it. Or maybe just 1 more problem. So getting pretty close. Not too long today.
You have to solve the check by yourself.
Yep, solve for X. Anybody have an answer? Anybody got it?
X equals 1.
So here's the thing, if x equals, well, no, that's not true. Never mind. The ratio, the proportion, the ratio would be 1. If they were exactly the same, that wouldn't necessarily mean that x equals 1 though. But anybody have it? Not 1. Not 2. Solve it. 1.5. Good. It's 1.5. All right. So right here, if you take the length of JM, I did it this way. Your equation might look different than mine, but it should still end up being the exact same answer. So I started the JM, which corresponds to QT. So that'd be 4 to 2. So 4 over 2. Oh, you got to make sure you know which parts correspond because there's actually 3 lengths given on this second triangle, and there's only 2 given on this one. So JM here corresponds to QT over here. 4 goes to 2. So 4 over 2 equals, and then LM, which is where the variable is, LM right here is the same as ST over here. So that would be 3. So don't use the 4 from the second triangle. So you're going to have 6x minus 3 over 3. Cross multiply, 2 times 6x is 12x, 2 times negative 3 is negative 6, 4 times 3 is 12. Add 6 to both sides, 12x equals 18. 18 twelfths reduces the 3 halves, or 1.5. Now, there's another way to do this one, and that's why I'm kind of covering up with my right hand. Both of these fractions can actually reduce. 4 divided by 2 is 2, and then both 6 and 3 are divisible by 3. So the other way that you could do this is 4 divided by 2 is 2, 6x divided by 3 is 2x, 3 divided by 3 is 1. So you could say 2 is equal to 2x minus 1. So you can simplify both of these fractions without the need for cross multiplying on this problem. Doesn't change the answer in any way whatsoever. It's just another way of doing it. Add 1 to both sides, 3 equals 2x. Divide by 2, you get 3 halves for x, or 1.5, same thing. So a couple ways to go about doing that one. So 3 halves or 1.5 is our answer for that one. Questions? The tricky thing about this one is that this right triangle, or this triangle on the right, it's not a right triangle, the triangle on the right has all 3 sides labeled. This one only has 2, so you need to know which ones to match up in order to actually write the proportion. So
T is equivalent.
Where at?
T is equivalent.
T is equivalent to M. Yeah, so we can actually just use the similarity statement to figure that out. So J goes to Q, L goes to S, M goes to T. So if you're talking about length JM, right here, J to M is 1 to 3 in the triangle here. So Q to T would be where it goes to on the other one. So those 2 correspond. And then these 2 correspond. All right. So here we go, perimeters. Talking about perimeters and similar polygons. Now, dealing with perimeters and similar polygons is actually the same mathematically as dealing with the lengths, because the perimeter is just the sum of the lengths. So the proportions should remain equal. So let's take a look. In similar polygons, the ratio of any 2 corresponding lengths is equal to the scale factor, or the similarity ratio, which means that you can write a proportion to relate them. This leads to the following theorem about the perimeters, because it doesn't change anything mathematically if you use the perimeters, because the perimeters are just the lengths added up. So if 2 polygons are similar, then their perimeters are proportional in the same ratio as the scale factor between them. For example, let's just go back to this one right here with these triangles before we move on to the next page. We said that we had a scale factor of 5 to 4, meaning that this was the 5, and then this one over here was the 4. So if we add together NQP, all 3 lengths on that one, we got 15 plus 12.5 plus 11.5. So the perimeter of triangle NQP is 39. The perimeter of triangle RST would be 12 plus 10 plus 9.2, so that's 22 plus 9.2, so that should be 31.2. So if we have a fraction of 39 perimeter here over 31.2 here, that should end up giving us the scale factor, which is 5 over 4. So 39 over 31.2. So 39 over 31.2 is 1.25, which is exactly the same as what we had before, 5 to 4. So the perimeters have the same scale factor as each individual side. Which makes sense because perimeter is just adding the lengths together, and lengths have that proportion hold true because we're still talking about distance from one point to another. So let's turn the page. Last one. Yeah, this is actually just one example with a lot of words. Okay. This actually won't take very long. Here we go. Use similar polygons to find perimeter. All right. Here comes Jeffrey. All right. So Jeffrey plans on going to the state fair this summer. Has anybody been to the state fair here in Oregon? Like the state fair in Salem? No. I grew up in Salem when I was a kid. So, and I lived like, at one point I lived just a few blocks away from where the state fair was. So I just walked there when I was a kid. So Jeffrey plans on going to the state fair this summer. He has downloaded a map of the fairgrounds that shows all of the attractions. Jeffrey plans to visit the concert hall, Ferris wheel, and the sports center. On the map, the distance between the concert hall and the Ferris wheel is 9 centimeters. The distance between the Ferris wheel and the sports center is 8 centimeters, and the distance between the sports center and the concert hall is 4 centimeters. So basically, he's got a triangular path. He's going to three places. Describe Jeffrey's path. Oh, well, there we go. Oops, I didn't even know that was going to be a question. Jeffrey wants to visit the concert hall, Ferris wheel, and the sports center. Jeffrey returns to the concert hall after visiting the sports center. What polygon can be modeled by visiting 3 attractions? Yeah, triangle. In fact, we could even draw that triangle. Oh, well, there you go. Next thing, draw those segments. Okay. So what appears to be what, though? Concert hall, I'm guessing, is going to be the microphone. Sports arena is going to be where the football is. And then the Ferris wheel is definitely going to be the Ferris wheel. So if we draw our lines between, here we go. All right, so there's our triangular path. Let's go ahead and label these as well. So label the concert hall as C. So there's C. Sports center is S. There's S where the football is, and the Ferris wheel is F. And let's get the distances in there as well. So it says the distance between the concert hall and the Ferris wheel is 9 centimeters. So C to F, 9 centimeters. Ferris wheel to sports center is 8 centimeters, so 8 centimeters there. And sports center and concert hall is 4 centimeters, so 4 centimeters there. Cool. All right, so those are all the distances. There's our triangular path. Find the total distance. So keep going with this. If the actual distance between the concert hall and the sports center is 20 meters, how far will Jeffrey have to travel to visit all 3 attractions, then return to his starting point? So here's what we need to do. I'll just tell you real quick. We know an actual length in real life, and we have the corresponding length on the map as well. So how far is it on the map between the concert hall and the sports center? Four centimeters. And in real life, it's 20 meters. So that means that would be like 20 over 4, which is 5, right? So however many centimeters it is on the map, you'd multiply it by 5 to get the actual distance in meters in real life, because 4 times 5 is 20. Everybody okay with that so far? So we're not actually comparing the units of measurement in any way. So if we're just talking about 4 centimeters on the map versus 20 meters in real life, that would be 5 times to get from a distance of 4 to a different distance of 20, right? Like if you took 20 over 4, that would reduce to 5 over 1. Now they actually are converting this in real life, which is a little bit weird to me. So I don't think they need to. Anyway. Because I think I think we can do this another way that wouldn't be as complicated as what they're making it on this paper. So, so what I would recommend doing here is, because it says right here, it is converting this to actual meters. I'm not a huge fan of that. And I'll tell you why in a little bit. So it says, because 1 meter is equal to 100 centimeters, then 20 meters in real life is equal to 2,000 centimeters. So the number they want there is 2,000. So the scale factor, the actual scale factor is 2,000 to 4, which would be 500. Now I'm going to show you how I would do this. This is, first of all, this is not how I would solve this if I was doing this by myself. The perimeter, I would use this though, 4 plus 8 plus 9. So the perimeter on the map is what? In centimeters. Yeah. Plus 9. 21. Okay. So on the map, it's 21 centimeters. So it says to use the perimeter to figure out the scale factor and write a proportion, let W equal. Okay. This is, again, I'm not a huge fan of how this one is working out. There's an easier way, and I'll show it to you in a second. You do have to set up a proportion. I would agree with that. I do like 21 over W. I would actually write 1 over 5, though. Here's why. So let's just go ahead and do another problem off to the side. And this is the way that I would actually do this if I was doing this one by myself, because translating between centimeters and meters is not actually necessary. That's an extra step that you don't have to do. It works, it's fine. But converting from meters to centimeters and then back from centimeters to meters again, like that's more work than you need to do. So here we go. Let's see, reality to map. The reality to map scale factor is 20 meters in reality is equal to 4 centimeters on the map. Okay, 20 meters in reality is equal to 4 centimeters on the map, which means that 5 meters in reality is equal to 1 centimeter on the map. Everybody okay with that? We are not going to convert from centimeters to meters like they did, because we don't have to. If you don't have to do the extra work, don't do the extra work. Make it easier. All right. So ours is going to be a 5 to 1. Okay. Ours is going to be a 5 to 1 as opposed to a 1 to 500. So if we're going with, so the perimeter on the map is 21 centimeters. We know that. So if we write an equation of 5 over 1 equals, this is reality up here, by the way. So that'll be X over the map, which is 21 centimeters. We can just solve this in one step. That's why I wouldn't do it the other way. This is a one-step equation. It doesn't need to be like a 4-step process converting from meters to centimeters, centimeters to meters, and all that. So X times 1 is X. What's 5 times 21? Yeah, 105. And if you look down here, they solved it by multiplying 500 times 21, which is 10,500 centimeters. And then they had to take their centimeters and divide by 100 to get back to meters. But look at us. We got 105, which is the answer, without converting. X equals 105, which is how far it is in reality, which is the correct answer that you see down here as well. But we didn't have to convert from meters to centimeters and then centimeters back to meters or anything like that. We just knew that the proportion was 5 meters for every centimeter on the map. And we kept that in mind instead of converting units. You don't have to convert the units. So 105 meters, which matches exactly with that with no unit conversions. So what the book does isn't wrong. It's just more than you need to do. So I would rather keep knowledge of what my units of measurement are. That way I can answer in my unit of measurement without having to convert the units in the first place. I find that to be more efficient. So I would recommend doing it that way. You can convert your units if you want to. I won't be doing that though. All right, that's it for your notes.